So good evening, thank you so much for coming today. Actually, it's our first HackHealth meetup. We were expecting 200, 300 people, but I believe that for the first one, people didn't know it, so I continue to spread the word for the second one, and I hope to see you for the next one as well. Who knows fusion? We see some mentors. 1, 2, 3, 4, 5. Okay, everyone, so okay, I'm going to just do a little bit of introduction about us, who we are. You are in fusion and physics. We are what we call actually global catalyst for corporate innovation and startup growth, and also creation of ventures. Our motto actually is to supercharge innovators. So we have our secret sauce with great technologies and methodologies to make it happen. So today we have some corpos who help us. We help them to actually imagine the future. We started 3 years ago as a fintech accelerator. Swiss fintech, they need to be here, obviously. Then we launched this year another vertical called PropTech and Smart Cities. So PropTech is all the technologies in real estate and properties, and Smart City, engagement of citizens on new technologies. And then the great vertical of LifeTech, we focus actually on digital health, MedTech, biometrics, biotech, genomics, etc. Great. Today we have few partners, so we have the fintechs, so more or less the ones here, okay? So we have the fintechs from the 3 years, and we have La Mobilier for InsurTech, Investis, and then some versus partner like Ebell, Global, Amazon, etc. I think we don't have any more. So I'm Adela, actually. I'm the executive director here at Fusion. If you have any question or you want to know anything about us, please come to see me. And also you can follow us on Facebook, on Twitter, and on LinkedIn. So today, we have 3 great... So we have this great application. So go here.
Just
go ahead.
Very briefly, basically what you do is you go on Pigeonhole at .at, and then you enter the password, which is HackHealth, which is the event that you're at today. And if that's not the right event, maybe. But anyways, you go here, and at the end, when we do the Q&A and the questions, so this remains here for the rest of the presentation. And at the end, when you go on the application, you will see all the questions that other people have asked. So you can actually vote up the questions that you think are the most relevant. And then we will choose the best questions, because if we have 50, maybe we can't answer everything, but we'll try to cover the most of the questions that we do.
Great, thank you so much. So today, as I said before, we have started the meetup HackHealth. So we have a lot of meetups for fintech already, and we decided to do one for the vertical tech. So today the theme is BrainTech. For the following ones, we are going to focus on genomics, I think, or biotech. So, we are going to discuss how technology has enabled the world of health and well-being to evolve. Because as you know, technology is an enabler, it's not an end on itself. And we will see some of the startups. So now we have Stuward, it's one of the startups of the LifeTech vertical. And you will see how technology can actually enhance people's life, especially in health tech. Okay, great, Stuward. So we have Stuward, is one of our fellows from FinTech. A big applause, please! Yay! You have the Madonna thing, you don't need the mic. Okay.
But I need that thing.
Yeah, but you wait.
Hello.
And then we have also Christoph from the Human Brain Project, it's all later. And then Marc-Olivier for Neurorobotics, who's actually trying to put some brains in robots, so he will explain us how. We have the 3 of them, and we start with Stuart. Thank you so much. Applause!
No. I don't need that. Hello, my name is Lee, and thank you very much for being here. Thank you to Fusion for putting this on. I'm not a scientist, and I'm not a doctor, but I'm a very curious entrepreneur. And I think some might even say that I'm a bit crazy entrepreneur, because I purchased a restaurant when I was 18, without any money. And that is really a story all of its own. I did create one of the world's first web-based telepathology systems that was used successfully by the US government and the Japanese government to consult on rare cancer cases. And more importantly, I am the proud grandson of this beautiful lady that had dementia. And one day I got a phone call when I was living in London from my mother to say that she finally went to the doctor. And I thought this was a good thing, because when you have dementia, the family members often have difficulties getting their loved one to the doctor. But unfortunately, my mother told me that the doctor said that she has 6 months to live. And for some reason in my gut, I didn't believe that she had that long, and she was living in America. So I immediately booked a flight and I went to America to be with her. When I arrived, in typical grandma fashion, with a smile on her face, she said to me, she said, "Lee, I'm going to be fine. I just have the flu, and I don't know what these crazy doctors are talking about." So I said, "Yes, Grandma, I know." Now, fast forward a week, and she would scream in the middle of the night from pain. And the very next day, she said to me that she had to tell me something. And she said, "Lee, I want you to know I'm not going to make it." And I said, "Yes, Grandma, I know." So she asked me to make her a promise. Actually, two. One was that I would take care of my mom. The second promise, though, was that I would use my technology skills to help people. And I said, "I promise." So I gave her a kiss, and I took my flight back to London. I said goodbye to her, literally the final goodbye. And I landed in London, and I flew down to Cape Town. And when I landed, I got an SMS from my father that simply said, and I thought about the promise that I made to her. And I thought about, how can I turn this negative, sad situation into a positive situation? And how can I use technology? I mean, that's what I do. And I was supposed to point it over here.
Yeah. No, right.
And so the first thing that I did is I put together a team, and I put together a company to answer this question. It's like, how can technology be used to improve the lives of dementia family caregivers? And that really is what we set out to do. I put together this team. Now again, not being a scientist and not being a doctor, and dealing with something such as dementia, I knew that really the first thing was to have the expertise. Now this is interesting in and of itself, and it was almost as if my grandmother was looking down, because I went to the doctor and I had a surgical procedure. When you go to the doctor, you have to fill out this form, and then they ask you, what do you do? What is your career? Well, I put on my form at helping dementia. And my surgeon saw it, and when I went in for the consultation, he's like, "What is this with dementia?" And I told him what I was doing, and he said, "I know the exact person that you need to speak to. Her name is Karen Barakovitz. She's the founder of Dementia South Africa, and she was a caregiver for her own mother for 21 years. So she became part of Stuward, and she introduced Dr. Celeste Dioger, who is renowned in the area of Alzheimer's research and in cognitive assessments. And so it's kind of interesting how that sort of played out. And with this team, the first thing that we started doing, ignore what you just saw. So the first thing was to look at as much research that we could find. We first started looking at dementia. Through that, we realized also that the family caregivers are also becoming patients themselves. And so from this research, it guided us into our own program where we wanted to go out and we wanted to interview family members that were caring for somebody with dementia. And what we wanted to do also is we didn't only want to interview them in a single country, such as Switzerland. We were really curious to know, does a person's culture have an impact on the level of burden that they experience, etc. And so we did just that. And this is one of the pictures. So we interviewed caregivers in countries such as Switzerland, or a very poor caregiver in a rural village in Africa. The burden that you experienced from caring for somebody with a cognitive disorder like dementia was the same across the world. And this led us to, somehow we jumped into this one, but this led us to 3 areas where we felt technology could really help. And the first area being personalized assistance. So how could we use technology to be able to help the family member with very specific tasks, such as remembering to remind the mother to take their medication, or to schedule doctor's appointments. The second area was centered around training and support. So when we get this job of caring for somebody with dementia, we're not trained for it. We don't know how to handle the situations that come up. And this is what is also causing the stress and the burden. How do we handle a situation where your mother no longer recognizes you or thinks that you're an intruder that has broken into the house and pulls a knife on you, which is one of the stories that we got. And then the second one, and I think about my grandma a lot with this one, is that it's easier access to doctors. It's difficult to get somebody with dementia to go to the doctor. With my own grandmother, they think they're perfectly fine, and then why are you trying to make me go to this doctor who's fine? And so this was the third area that we looked at through telehealth. And so we designed a platform where the platform starts with understanding you as a caregiver and your unique situation. What is the context of your care? Is the person living with you? Is the person not living with you? What is your level of knowledge about the condition that you are caring for, et cetera, et cetera, et cetera. And then based on this information, it then feeds into what we call virtual care managers. So it takes that and it designs a personalized care plan for you and highlights areas where you are weak or need to focus. And then in addition to that, it matches you with a coach. A coach either being a former family caregiver who has gone before you, or a professional such as a social worker or another caregiver. And this is a hybrid between a chatbot and an actual person that will guide you through your situation. And here we've gotten a lot of information. We've gotten a lot of situations where they wanted information around how do they make the decision to put their mother into a care home. And so the journey really has gone from what are these unusual behaviors that I'm seeing, and is it some form of dementia like Alzheimer's? All the way through, the mother has passed away, how do I deal with the fact that I no longer have this daily responsibility? And then easier access to doctors through telehealth and video consultations. And this is an area where we wanted to look at it from both sides. So we wanted to look at it from the family member, the caregiver, and the person living with dementia, and the health professional on the other side, because everyone had to have an incentive to use it. And me being a data dude, as some people
I like the name.
call it,
Data dude.
Data dude.
Data
The entire system is a learning system. So we are using data, we're using lots of inputs, and the idea is that Stuward, he will get smarter and become more valuable to you as the caregivers, to you as the doctors and the medical professionals, as more people use it and engage. And now, Grandma's promise. So what, in the beginning of this talk, also turned out to be a very down, sort of negative situation, has actually turned into a very positive situation. And I'm proud to stand here and say that we have been recognized by many different organizations. We have won awards, and I'm sure my grandmother would be very proud. And I encourage all of you to also, in your own lives, how can you use technology? Thank you very much.
No questions? No idea. Thank you so much. So, if you have any question, put you in the application, and then at the end we will be able to respond to it. I have the power.
Okay, great.
Okay, cool.
These microphones.
Have to
yes,
shoot.
It's one of my tech peeves, if you will. So if there's a startup here who can make those things work like 100% of the time, I think we can make a lot of money.
What is his name?
I know. So I don't know. So hi, good evening. My name is Chris Ebell. I'm the executive director of the Human Brain Project, and I think we have a couple. Yeah, that's us. I should just do the next one already. Oops.
I have to put it. Actually, I'm the one who's here.
Sorry, you're absorbing all the
Yeah, I'm
information
sorry
here.
on the bios.
Okay, great. So what I'm going to do is in the next 15-20 minutes, I'm going to give you a quick overview of what we're doing. But I'm going to focus it on the health aspect because it's a health hack. And I believe that I can give you some examples, some pointers of where what we're doing can actually benefit some of you, and I'd be interested in talking to you about where we can actually provide value to you. The project is a massive project. Actually, it's a publicly funded EC project. One of their flagship projects. That's one. The FET is a program. The European Commission says Future Emerging Technologies. So this is what we're doing, and the flagship means that what we want to do is we're going to basically use ICT to advance our knowledge in brain, in any area of brain research. But we're not doing research, so we're doing a lot of research ourselves, but we're doing research that we're doing is to build that platform, to build that infrastructure. And actually it's a service that we want to open to the community to actually do research on. Now, I don't actually see my slides in front of me, so, oh, I do actually, yes, okay.
Very small, but
So, no, that's okay, that's enough of a pointer, isn't it? I was kind of flying blind here, so, so what we're doing in terms of, if you're looking at this very simply in terms of what we're doing for for industry in the widest sense. When I say industry, I mean really massive pharma to startup. It's the same, I mean, the mechanisms are the same. So what we're trying to do is we're going to try and get the risk down and discovery up. So these are the two things that we have basically on our flag here. And I'm not going to actually go through the, oh yeah, here we go. This is where we are. This gives you a little bit of an idea of what our tech roadmaps. I'm going to just pick some stuff out of that later. So I'm not going to actually ask you to read the whole thing. It's a little bit of an ask here. But what you can see in terms of technology, maybe that's the second row here. What we're doing is, we're doing modular, we're basically using modular computing. Modular means we're using high-performance computing. We have 6 of the top high-performance computing centers in Europe. We have 2 different very large neuromorphic systems. And we're going to actually go into try to get potentially some quantum enablers as well to kind of go in that direction of looking at large-scale optimization problems. But this all sounds a little bit. I mean, it's cool because it's very techy, and if you look at where we're going here, we're really looking at brain-inspired hybrid systems that are going to replace essentially a lot of the computing as we know it today. So in going in that direction, but all of this isn't really just to build the compute facilities. It is really what we're doing together with neuroscientists. Okay, so that's the cool part. We're actually bringing biology and this kind of computing power together. And this is sort of this hybrid that if you want to talk about what artificial intelligence actually is going to look like in 5 or 10 years from now, you're going to look at something like that. And just to kind of tell you that we're not just the next kid on the block who's trying to build an artificial intelligence, or we're not even saying that we're doing that. We're just saying that to kind of position the whole thing a little bit. But what we can do is we can actually tell you when somebody tells you, oh, this is artificial intelligence, that's what we're doing today, we can actually help tell you like what it actually is, what they're saying, and how is this actually what it is? And will this perform to those standards? Is it safe? So that's the kind of stuff that we can do with that. Now, the human brain is in itself a very, very complex organ. It's the most complex organ, probably one of, if not, what are we saying, Marc-Olivier? It's the most complex system in the known universe at this point. I mean, we don't know anything more complex than that. So it's kind of it's a little bit of a challenge to break that and decode that. And when you look at this here, what you're seeing here basically is these are the levels, the size levels really of the brain. The challenge itself isn't necessarily to understand this level or understanding this scale understanding of the human brain. And that's really tough because those go really across. If you're looking at this here, we're talking about probably centimeters, 10 centimeters, 12 centimeters. If you're looking at behavior, you're looking at meters and the Earth. And down here, you're looking at nanometers essentially. So this is the orders of magnitude that you have to bridge here. And also, by the way, the brain not just scales in space, but also scales in time, right? Your brain begins with the first, basically at conception more or less, and then kind of goes on until you die, right, and decay. And in between that, your brain is never the same. Physically changes every second of the day, and every single thing, every impression that you hear changes your brain physically. And so that really makes you a different person in a way every second of the day. And looking at that in terms of all of those scales, we're looking at a pretty complex challenge. I mean, the problem here is now, if I talked about this just quickly, why we're not, so we're saying this is a research project. Are you doing research? What's your goal? Okay, I talked about the multi-level situation, which is a goal, but there's a problem with research projects. They're great. I mean, they're doing stuff, right? But if you follow a regular research project, essentially you could fund this whole, right? And our project is funded around 400 or 500 million right now from the European Commission, and we're expecting another 400 or 500 million from member states, maybe a little bit more. But even if you invest 1 billion in this whole brain initiative or in this whole brain research project, you're not going to actually get there. What's happening is you're going to get a publication out of it, not one, but maybe 100, 200, 500 great publications, but that's going to be it. So you've added to that body of 100,000 per year, and probably some really cool stuff. But it doesn't really scale up. It doesn't scale to where we need to go in order to actually get a little bit of a handle on this. So like, there's a question that I ask a lot of times when I talk to people. It's this one here. What is the cost of finding and confirming one potentially clinically relevant fact about Alzheimer's disease? Okay, so what's the rough cost here? Okay, what are we talking about? Any ideas? Roughly?
50,000.
Yes, 50,000 euros. 500 million euros. Okay? So that's and maybe it's 400, but that's the ballpark situation we're talking about. So our project is funded with 400 million right now, with 500. So like, are we gonna understand the human brain with that kind of funding? Probably not, right? So we got to get smart and think about, okay, how can we actually still, help doing that? So we need to scale, obviously, but we're kind of out of money right now. So, we're not, but we would be if we did the whole thing. This one, this is like 1972 or something like that. Parker or something you can find it in your textbook. But what I'm saying here is, there's a problem between the resources and the research, and then we're not even talking about this here. Basically, if that would be our premise, we would still kind of be stuck here. So we talk about this a little later. Now, here I talked about the challenge. I'm not going to go into this again, but just for this is good stuff. You can actually get this. Since you're here, you got to learn something. Okay, and you got to go home and say like, okay, look, did you know that the brain has 86 billion neurons in it? It's super complex, a lot of those. And each one of these has 7,000 synaptic connections. So you multiply that, and you get a lot of connectivity that you can probably potentially look at, right? And decoding that, I'm just making the point again, like this is really complex. Did I say that? Okay, so what are we doing about this? Okay, here's our approach that will actually make this a little less of an intractable problem. So if you look at this, and I really very much related to Lee's presentation when he said this is a learning system. This is kind of what we're trying to do as well. So what we're doing is we're building a platform, an infrastructure. So instead of saying like, and I just made up this example before when Marc-Olivier and I talked about it. So basically, instead of our scientists are a bunch of ice skaters, like figure skaters in the Olympics, right? And all they want to do is they want to win Olympic gold, right? That's the Nobel Prize in the science world, right? It's an amazing publication. But what we're trying to do is we're trying to build a stadium for them where they can do that, where not just one or two, instead of funding one or two of these guys, we're building a stadium where they can do that, where many, many of them can do that, and hopefully we get a couple of Olympic gold medals out of that. So that's kind of the idea behind this. And that kind of scales because we don't necessarily know, even we have some amazing people in our project, really great scientists. We don't know if that's really the Olympic team, right? Are they the best ones in each of the disciplines that we work in? Probably not. But these guys can now come in and use those systems. And what we're doing basically is creating a unified joint platform that brings together neuromorphic computing, it brings together high-performance computing, it brings together the Neurorobotics platform that Marc-Olivier is going to talk about quickly afterwards, to make academic and industrial brain research actually a reality, and you can use that over and over and over again. And the cool thing about it is that every time you're using the platform, I'm just literally repeating what he just said, it gets smarter, because we have, for the first time now, and I was in a meeting in Munich where we talked to some of you about this, where we had to tweak a little bit some of the approach that we did in the medical research area. And for the first time, we really codified that into our research program, that we actually built in learning mechanisms that take the knowledge of each run, essentially, codify that, and make it available for future use again and again and again, both in the technological but also in the human space. So that's what's happening. So basically, we're building a platform based on some of the cool, on the best technology that's there, and this is obviously not some of the best technology, because I messed up a little bit my slide here. I'm trying to salvage this right now, but I don't think it's work. So what we're bringing together is people, data, software, and computing resources. That's really that's the ingredients really that you need to do, and that's literally all it is. Okay, it's kind of simple. You know, it's like a lot of times when you make food or when you cook, I don't know if you guys cook, but if you do that, a lot of times the simple stuff is really what really comes out the best, right? So kind of very few ingredients, but you got to mix them together in the right creative way, and that's what the challenge really is. Now, in terms of mixing together what we have, and maybe, I don't know if you talk about this more over, but like going in there, and this is kind of where I'm starting to be concrete and want to invite you to go and use our systems, is we have a collaboratory that's an online collaboration platform that gives you access to a lot of those resources, right? So you can actually go in and, Marc-Olivier, can we use neuromorphic or neurorobotics platform? Can we use that? Can people use that?
People can use it. Yeah.
People can go in there and use it. You can get an account.
There's a demo that's easier to see because.
Right, but I mean that's the kind of stuff I want you to actually go there and have a look. You can use neuromorphic computing resources online, and you can see what you can do with that. So there's stuff that is actually doable, and so we have also the brain data is web accessible. You can go there. You can go have check the atlases out. These are 1 micrometer atlases of the human brain, including directional, you can see what direction the fibers are going. This is like the cutting, that's the bleeding edge of, I'm saying bleeding because there's less that stuff actually. That's actually what's available right now in the market. This is what we have. We have unmatched computing power that is unique in the world. No one has that kind of computing power right now. And this is really frustrating because that's not it's like literally the slide I was kind of. But okay, let me try. You know what? Sometimes you gotta be creative.
Exactly. Use your brain.
That sum here is actually the what we can do with our systems. But I can, I'm just gonna go through this real quick with you. So what we do here we have data scientists, we have theory people who write theory and algorithms. You gotta imagine if you're going to do a brain simulation, and this is a big one, you may have heard about the project in terms of simulating the human brain. You may have seen that. It's still one of our big things that we're doing. But you got to have people who write those algorithms and tell you what's the theory? How do the different layers now relate, and how do you codify that in actual code, right? So if the neuromorphic research, and we have plus artificial intelligence, and this is the basic system, high-performance computing, analytics, neuromorphic, and we're going to do some quantum because it's kind of cool. We have to these days, but it's actually cool because I'll tell you about the modular part and how to bring this together. So the idea, of course, is not just to use one type of computing, but really bring them together in a smart way so that you can attack the really difficult questions. Now, what can all of this do? And I think there's one application that's left here. The rest got killed. I don't know who messed with that, but this is, it's good. I mean, I'm learning something too. So applications, for instance, and this is one of the things that I just want to point out to you, and I actually have a list of a couple of use cases afterwards, but one thing I just want to point out to you, because everyone talks about artificial intelligence these days, and barely anyone knows what it actually is. And even the folks who are referring to it on a regular basis, or experts or pundits on it, a lot of times they're not telling you what they actually mean. A lot of them are referring to machine learning, but a lot of them are referring to some generalized human-like intelligence and so on and so forth. But if you imagine right now, if you look at Google or YouTube or these guys, they have all those algorithms promoting content, right? But we don't know what that algorithm looks like. We don't know. I mean, that's the thing, that when you have all the tech companies will not tell you, especially the big ones, they will not tell you what artificial intelligence actually is. It's going to be a black box. What we can do is we can crack that black box by building parity systems that are like that do the same thing, that can understand what kind of artificial intelligence we're looking at. And that's important because it gives you the transparency that you need to actually regulate the market, to actually make it safe in a way. And that will be one of the most, I talked about de-risking, right, at the beginning. That's going to be one of the most important things that will enable innovation in the health idea here. It's like a super boring slide, but let me tell you why it's important. The question is sometimes, you know, if you're in a health space and you say like mental health disorders, like brain disorders, you look at something like depression, right? For instance, how do you diagnose it? You go take one of those. The doctor's going to take one of those manuals, the DSM-5, and it's going to go look it up and say, okay, here are the symptoms. And it turns out that a lot of those symptoms are actually, they're just phenomenology. We don't actually know what's behind that. We don't know. And a lot of them just basically come from like 19th century science. I'm going to be a little mean here. I hope there are no doctors in the house. But you know, a lot of that is really legacy work, and we don't really know the biological basis of that. So a lot of those diseases are actually not one disease, but like 50 diseases, and we should be able to better classify those based on the kind of research that can happen in our systems. And then also, based on that, we can find better ways of approaching mental health or brain disease in actual fact. And you know, there's so many examples. I talk with patients a lot, and also patient families, by the way, which is the black matter of the healthcare system, where no one really talks about that, and you really need to empower those folks as well with information that's actually valid. So here are a couple of things that we can do. This is the last slide, and these are random use cases that you can think of. But there are also, all of them could be ideas for businesses, right? I mean, this is not just stuff that is a matter of research or basic research, but there is also a lot of this stuff can also be looked at in terms of providing solutions to problems that can actually go also in the marketplace. When you look at stuff like this here, precision-guided brain implant placement. I mean, these are medical technology right there, where you actually directly influence outcomes. And we have some clinical trials going on in this area, and that's where all systems of our platforms come together, right? You can simulate, you can measure, you can see how this is going to work in the brain atlas, etc. So you can really directly impact medical outcomes here. You can imagine that there are a whole bunch of other applications of the project or of those kind of systems. So I kind of focus a little bit on the healthcare space. What we're seeing right now is an incredible interest also by startups. I went to Israel twice last year, and we had a couple of really good interactions. I did a bunch of one-on-ones with companies. Something we could also think about here, where people basically come in and say, like, this is what we're doing. This is the technology we're developing. Here are the data sets that we're doing. What can you guys do with that? And then we have those conversations, and then I bring them to our own providers. I go, like, we're trying to build up in our next phase a kind of an innovation concierge, like an HP concierge system, where people can go and say, like, this is what I want to do, and like, how can we get that done, and how can we build a knowledge supply chain inside of the project to actually action that. So that's kind of a little bit what we're getting at in the next couple of months and years, and hopefully we'll see some of you guys to be part of that journey. That'd be great. So thanks for listening, and then I'll just pass on that.
Chris gave you a very broad introduction of the Human Brain Project, which is a massive project in terms of what it does, and neither he nor I'm an expert in all the facets that the project has to offer. So I will talk about two of the, many different aspects, which is called Neurorobotics. And I will also try to draw an arc from, you heard it already, from brain simulation, what that is, and what it isn't, to Neurorobotics, what it is, maybe what it isn't, and what it could be useful for. Yeah, we are in the act of finding that out ourselves. That's why it's research and not yet, but maybe.
Here. The clicker here. Yeah.
Okay.
Yeah.
No, I didn't actually press it.
Okay. I thought you were free.
So it's still here. So this is one of the older slides from the Human Brain Project. illustrating a little bit what the scientific goals were. And I'm talking about this part here and this part here. This is called accelerated neuroscience. And one of the motivations for founding the HPP was that there is a huge amount of data about the brain out there. In fact, so much that nobody really knows what we don't know and what we know. Yeah? And if you are a scientist, a doctor, somebody just interested, it's very difficult to find out, for example, how many neurons or how many cells do you have in your brain in a particular region. The interesting fact is nobody actually knows. You know, we're trying to build artificial intelligence, and you take one of the most studied laboratory animals that we have, a mouse, and you ask, how many nerve cells are there in the brain of the mouse? That's a question that maybe 5 people in the world can answer you, and then if you just cut out a little piece of that brain and say, okay, this is a part that is responsible for your eyesight, and ask, so how many cells do I have in there? Nobody knows. Yeah, it's a very curious fact. So the idea was build something where we can collect all the data. And the other thing is, while we're at it, we might as well try to learn from the brain how to build better computers and how to build robots that have brains and not just deep learning algorithms that somewhat work, but not really. And the solution here was to have a collaborative research infrastructure. And Chris outlined that, and I tried to fill that with life in one of the many domains that we have in the HPP. And now I'm trying to switch again. Yeah. So integrating all we know about the brain, and HPP was often criticized for its impossible task. And the metaphor that I always use is the first globe. That was created in 1492 by a German. He was called Martin Beheim. And actually at that time the word globe didn't exist. That's why he called it the Erdapfel, which means the earth apple. But incidentally, it's also in some German dialects the word for potato. Pomme de terre, yeah, literally in French. Yeah? So this is pomme de terre in German. Also literally. Yeah? So basically what this guy did is he took all these maps that existed at that time, they were all hand-drawn from merchants, travelers, and literally arranged them on an empty ball. Yeah? And this is actually the original globe. It survives. You can visit it in Nuremberg, in Germany. And you can see, for example, this is the outline of Africa. And if you consider the time, it's actually pretty good. If you look at the encyclopedic knowledge that you found drawn on top of this, this is completely absurd because nobody actually visited the inside. And this is kind of the state of knowledge of our brain that we have. There are certain areas which are well visited, like in this case it would have been Europe. You probably had a pile of maps from Europe, and it got very sparse if you go somewhere else. For example, if you look at this picture here, so this is a drawn version of the same globe, yeah? And here you have Spain, this is Africa, the west coast, this is Spain, this is Ireland, England, and this here is a country called Katai. Does anybody know what Katai is? It's the old word for China.
Okay.
So if anybody read Shogun, that's what they call it. This here is supposed to be what? Can you guess?
Japan?
This is supposed to be Japan, right. And we all know that something very significant is missing in the middle, yeah, because 1493, Columbus hadn't really returned yet with the news that something is happening in between here. Yeah. So this was a compilation of the knowledge of the world at that time. It took Martin Beheim quite a lot of time to compile this. This is Google Earth as we have nowadays, and it took roughly 500 years to go from here to here. Yeah, and the brain, as Chris has explained, and I try to illustrate that, is vastly more complex in the sense that we don't have to worry just about the surface like here, but we have a three-dimensional thing with lots of complex pieces inside. Collecting the data is vastly more difficult, and actually we don't really know which which slide next? Okay, so the question is that actually possible? Yeah? Can you, A, collect everything that you know about the brain, and B, can you use it for something, actually? And criticism that we've heard in the human brain project very often is you cannot simulate the brain because we simply do not know enough. And that is, of course, under the assumption that the simulation is only useful if you have the complete knowledge. But what if you turn the argument around and say, okay, why not use a simulation to find out what we actually need to know next in order to make things better? I mean, after all, if we started with climate modeling after we know the weather and the climate, it would be a bit defeating the purpose, right? I mean, we started climate modeling 50 years ago when the supercomputers had less computing power than your mobile phone, yeah? And it was useful, and you have to get into the habit. So the mantra that we're always preaching is that you basically build a tool chain that turns data into models, yeah? Similar to what we do in climate modeling. The first models, they have to be coarse by definition, they're very rough. And then you validate the models against the data to refine them. And what I teach my students always is a bad model is still better than no model. Because if you have no model, you can just guess. But if you have a bad model, you can at least measure how good or how bad it is. And then you add new data sets. And since the human brain, we've seen the numbers, 86 or 100 billion cells with a huge number of connections. This is something that is beyond the capacity of modern computers, so we start small. Yeah? We use a mouse brain, 75 million neurons, roughly. I told you, people disagree about this number. And this is 10 to the 10, that's 10 billion synaptic connections, 10 billion, that's the one with 10 zeros, yeah? Or it's about the budget of the United States. Anyway. So, and here we are again with the question, where do you start? Yeah, so you've seen a variant of this picture here. Chris presented it down here. You have nanometers. That's 10 to the minus 9 meters. This is basically a few hundred atoms. Yeah? Creutzfeldt-Jakob disease, mad cow disease for the older ones among you, originates down here. Then you have the chromosomes, they're actually larger, then you have the synaptic connection and so on. You go all the way up to the meter scale where you have an entire organism. And the brain is organized across all these structures here. And the question is, can you build a model across all these levels? And this is something that the Blue Brain project here in Geneva has pioneered, and they target roughly this area and build and reconstructed something that is called a neocortical microcircuit. This is this, this looks a little bit like an old toothbrush from the top. It is literally neurons put together back in space. This is a little video that demonstrated. So this is one nerve cell reconstructed under a microscope, and we have many, many of them, and we basically try to put them together in a computer like they were in the actual brain. So this is now a rat. What you see here, this is roughly 0.5 millimeter, and the complete size here is like 2 millimeters, just to give you an idea about the size here. This illustrates how things are put together, and this gives you a reconstruction of a tiny part of the brain. This will fill up completely because there is no free space in your brain. So this was one exercise, of course. This is a bit limited, and you have to limit it in the fact because you have to actually measure all these morphologies here, the different shapes of the neurons. So the technology has to be advanced so that you can scale the whole approach up, and this is what is being done in the Blue Brain project here in Geneva, and also in the wider context of the Human Brain project. So I'm fast forwarding a little bit, I hope. So this is a simulation here, and it's also a bit messed up because you see it's a bit stretched in length. The color here is the electrical activity. So this is a simulation. What is a simulation? A simulation is simply a model that is running in time. Yeah? It's like an animation. And now the idea is if you integrate data, you integrate it into a database, and this is also kind of strangely scaled version here. Basically, the idea is you have a brain, and at each position, and this box is actually supposed to be on this brain here, you can break it down into the different components that we have. And this can be used then to create a brain model. Let's see, if I have this, yeah. So basically what we use is we use a simulation of the brain that we get from there. So every dot that appears is a neuron that is sending its signal to other neurons. The color here is the brain region where that neuron sits. And up there you see a time scale in milliseconds. A millisecond is the thousandth of a second. So you've witnessed half a millisecond. And this simulation here, to run it, actually requires a supercomputer. This is not something you run on your laptop. This is something where you need, in this case here, something like 128 computers with sufficient memory and everything like this. So here we've witnessed the activity of a tenth of a second. Of course, if I played back in real time, you wouldn't see much. Yeah? And the problem now is this is a simulated brain, but can you actually can you tell anything from this? No, there's just a few blinking dots. And let me show you something else. What about this one? Yeah? So if here we have a little mouse up there, it's stimulated, you see something blinking here, there's some causality, and what it tells us is you don't, just having a brain that is sitting there, it's relatively boring. It needs a body, it needs its natural habitat, it needs a home. And this is what neurorobotics is. It's trying to take these brain models and put them back where they belong, into a body, because our brains have evolved in the end to run literally a body through its life. And I'm coming back now to the, I think so at least, to the research infrastructure. So if you look at, so this is now an X-ray picture here through a mouse, very simplified. So this little bit here is a brain that you've seen, and neurobotics means that you have to take care of all the rest, which is actually quite smart, because here you have your spinal cord, which is responsible for taking the complexity out of your movements. Yeah? For example, if I stretch my arm, I have 1, 2, 3 degrees of freedom, my joints here that I move, but I have also like 20 muscles that are involved in doing this. And of course, our brain doesn't want to worry about how do I actually have to use 20 odd muscles to stretch my arm. My brain only thinks I want to stretch my arm. And the rest is done down here by these little wiggly things here. These are little circuits that take care of this. And this is your neuromuscular system. So what we have to do in order to give our brain a body again is to give it the kinematics of your neuromuscular skeletal system, as well as the sensors that are distributed around the body. For example, touch. A mouse wants to use its whiskers, you have the eyes, the nose, and so on. So this is what neurobotics is about, completing the picture and reconstructing the different senses and creating different behaviors. This is what ultimately we're interested in. And there's another interesting aspect, namely, you see here's this brain in the background, and in the foreground you have all the different functions that you might associate. And if we talk about theory or artificial intelligence, it's always about these blue bubbles here. Yeah? It's about, for example, memory and learning and controlling things. But in the back we have these lot of blinking dots, yeah? The brain as a biological organ. And what science still has not solved is, how do you connect these blue bubbles with the brain that is behind it? And this is ultimately the challenge that with the tools in the Human Brain Project we can address. Because different types of brain models, the theoretical ones, which would be more in the AI domain, and the biological ones, they can coexist and control the same body at the same time. Yeah, so that's again just an illustration of the way we in robotics, namely that you have, for example, an experimental paradigm. And this particular one is a paradigm for stroke recovery. So you have a mouse, it trains it learns a task, a stroke is introduced, and then you check different paradigms for recovering from stroke. So you can do that in a physical experiment, you get a set of data, or you can do it in simulation. And here you see our brain model, and this is our simulated mouse in the very same experimental apparatus. And ultimately, not now, this is a little bit looking into the future, ultimately you can use our infrastructure to test different paradigms, even personalized. So the toolchain for building brain models eventually should develop into a stage where you can go into a scanner with your particular stroke, or even you have a pre-stroke picture, and you get your personalized brain model, and that allows doctors to plan therapies well before they actually have to do an intervention. So there's a certain workflow. I'm not going through that, I just want to show you. Okay, so part of our infrastructure here is what we call an environment designer, so you can build your virtual laboratories from components. It's a little bit like an IKEA tool, but a bit more involved, of course. And I'm forwarding this. There's one, this is more interesting here. This is what we call the robot designer, but here we literally, we build the musculoskeletal system of our mouse. Now, why is this something you might want to do manually? Because there are certain cases where you have, for example, how do you say that in English? Misgrown muscles or bones and structures like this. And for example, with a tool like this, you can paint on the muscles. For example, you can plan a repositioning of muscles and test out how would that affect the ability of a patient or an animal to move. Doctors are already doing that now. You can check it out on YouTube. There's a number of interesting videos. We have a similar tool like this. And then you go into the simulation in our Neurorobotics platform, and this is now here our virtual laboratory, and it's a high fidelity 3D environment. It looks like a computer game, but in fact there is physics simulation behind all these objects. And here you have a mouse moving a lever, and this is now a one-to-one reproduction of an actual experiment. This is a prototype, so there is no brain here. All the movement that you see here is purely your spinal cord being activated. The attachment of the brain model is something that we are right now doing. And here you, for example, measure the forces that are applied by the mouse here on this apparatus. This is a prototype of our brain. You see it's far from having 100 million neurons here. This visualization is just to demonstrate how these things can be connected. One more. And now this is the final video here. It shows another use of the Neurorobotics platform, namely for prototyping robots and how to train so-called control algorithms for robots in simulation and then apply it to physical robots. So why would you want to do that? Because, let's say you are a company or a university, robots are expensive, you only have a few of them, but training and learning and developing algorithms in simulation speeds up your development process. So here you have a little robot, and it's a so-called compliant robot. That is, it's built from soft materials, which with traditional control algorithms are very, very difficult, if at all, to control. And here we use a so-called evolutionary algorithms to learn different gait patterns for this quadruped robot. So eventually it will be able to learn, and then, so this is now here 5 times accelerate, and you see here this is generation 86, so basically in each iteration we do a random, I pressed the wrong button now you have to watch it again. If you want to see the real robot doing the dance, but you can trust me that it will do anyway. In the meantime, this is for the geeks among you who understand what a covariance matrix adaptation is. This is a little robot here, and basically jumps around, and in the end, so this is the virtual equivalent of this guy, and in the end we basically take the algorithm that was developed here by basically trying out. And an evolutionary algorithm is nothing but a fancy word for trial and error. Yeah, it's optimized trial and error. And we can just run that automatically with our simulation platform here. And then I think the video ends in showing how the same algorithm is then used on the real robot. So here's generation 86 where we were. It starts getting useful here, what we see. Then this is a bit of the technology. There are different gates. This is a hopping gate. And this is actually a little brain model here that produces this. The camera is a bit shaky because there is no camera person here, but the camera is kind of artificially glued to the center of gravity of this little box here. And then, okay, yeah, it shows you how you can play around with this model and do all sorts of things. And I was hoping, it's a while ago that I shot this video, that it shows you the actual robot moving around, but maybe I have to fast forward. Here we go. So this is now the hopping gate on the little robot here and in the simulation. Robots like this are interesting because it just costs a few €100 to produce. They're much, much cheaper than other robots. Okay, so I think that was actually here the rest of my presentation. Yes, it was. I hope I didn't talk too long. Thank you very much.
Thank you.